Welcome back. This is homework 1, part B. Starting with question 1, we will be deriving the wall thickness T as it relates to PHR and tensile strength for a cylindrical tank. We can start first by drawing the tank. What's going on? We can do a section through this so we can see it better from the middle. Looks like this. And we can label this as H, this is R, and this, usually I'm able to undo. I'm not sure why it's not working. And this is T. To find the tensile strength for the internal force, it's assumed to be equal and opposite at the half point. That's why I cut it in half. And we can find it by doing the area of these times our tensile. And the area of these is going to be equal to height times thickness times 2, because there is 2 of them, times your tensile strength. So we can leave this here for now and draw another diagram of the top of the cylinder, and we're going to want to find the force due to pressure, and we can find that by doing a cross section. If I were to draw it on here, for sake of matching, it's like that. Well, you get the gist. So we can start by writing, or we want to integrate the difference of force, and that's going to be equal to the integral P times the differential area, which is going to be equal to pressure times R d theta, this cosine theta, times H to get this aspect in. And we are going to integrate from here to here. So write that. So actually integrating, we're going to pull out our P and our R and our H because those are constants. My undo feature's back. Interesting. So now we are just left with cosine theta d theta with our limits. And the integral of cosine is sine, so our force is going to be equal to P R H sine theta from negative pi over 2 to positive pi over 2. And when you plug in pi over 2, you get 1. When you plug in negative pi over 2, you get negative 1. So this is going to equal 2 times P R H or 2P R H, and we can circle this, and we are able to set those equal to each other, the two yellows that I called out. 2HT tensile is equal to 2PRH. We get to cancel the 2's and the h's. And solving for thickness and how it relates is going to be T is equal to PR over tensile. And we get to box that in. And that is problem 1. All right. For question 2, we will be doing the same thing, but with a spherical tank instead of the cylindrical one as last time. I already drew the sphere, so here is a axis with our z dimension, our y dimension, and our x dimension. We will be taking the areas of these guys. It is useful for me to write which one's which. This is theta, and this one is phi. This is theta, this is phi. So then we can label these sides as sine theta and sine phi. Alright, so there's that. We will want to take the force in the y and derive integrate the differential force, and that is multiplied by both sine functions that I just labeled to the side. We can expand the df to p times dA, and the dA in this case is going to be r times sine phi d phi times r d theta, and then times what we initially had, sine. I guess it's important to note this is r. Fy. Now our limit of integration this time is on the y dimension, so it'll be 0 to pi. Then we can begin, I guess write that here, 0 to pi. We can pull out our constants, which is PR and R, and then we will take this and this together, and then this and this together, and integrate separately. I guess I could, like that. And might as well for differentiating. So we can integrate 0 to pi, and we already said to pull out the p r squared to the front because they're constants, and then we get sine times sine squared phi d phi, and then like this d theta. All right. Okay, so then we will attack these separately and then bring that back in after. So our sine squared phi d phi is going to be equal to 1 minus cosine 2 phi over 2. That is a trig principle. And then when you integrate this from 0 to pi, you end up with 2. I think, yes, yeah. That was a constant that I had looked up prior to making the video. And then we can, this one's a bit easier, sine theta. D theta is going to be equal to 0 is equal to negative cosine theta from 0 to pi, which is equal to, no, I think I got them mixed up. This is pi over 2, and this is 2, because this one was the negative cosine of pi is equal to 1, and then negative cosine of 0 is negative 1, and that ended up equaling 2. Okay. All right. And then those multiply, so you end up with pi. So your pi gets multiplied by your PR squared. So we are left with PR squared pi. And like we did with problem 1, we are going to do this here, but instead of this, it's going to be our area, which is going to end up with is this here, and it is the tensile strength times 2 pi r times the thickness. So if we look at the r times the t times the tensile and times your pi around, it gives you the cross-sectional area. And then again, we can simplify. Our pi's cancel, one of our r's cancel, and that can be rewritten as PR equal to tensile to t. And again, we're solving for t, so we can simplify as t is equal to PR divided by tensile times 2, or like that. And that is our expression relating our t to these variables. So for this one, we are comparing the cylindrical and spherical tanks. Cylindrical, your thickness is going to be equal to PR divided by tensile, and your spherical is T equals PR divided by 2 tensile. So if we bring our tensiles to the other side, you see that and you swap the T and the tensile. Divide, doing both sides at the same time, confusing myself. So you see that for the same equation, the spherical has twice as much tensile as the cylindrical, and the spherical would be a stronger force for the shape given.